Welcome back to the deep dive. Today, we're going to do a deep dive into the world of manufacturing processes.
Ooh, fun.
We've got a whole stack of academic lectures and transcripts here
Okay.
that really get into the nuts and bolts of how things are made.
Right.
And we want to understand those core processes. What are their advantages and disadvantages?
Right.
And how do the properties of materials play such a huge role in all this?
Yes.
Get ready for some surprising connections.
You might be surprised to learn just how much the properties of a material dictate what you can do with it.
Okay.
A tiny tweak in something like melting point can completely change your manufacturing game plan.
Okay, so before we get into specifics,
Sure.
let's define manufacturing first.
Yeah.
I mean, it's more than just making stuff, right?
Absolutely.
Yeah.
Think of it as a transformation process.
Good.
You start with raw materials, say a big chunk of metal ore,
Mm-hmm.
which isn't really useful on its own. Then, using various techniques, you transform that ore into something usable and valuable, like the engine in your car.
Right.
That's manufacturing in a nutshell, adding value and making life easier.
And the goal is to do that with as few resources as possible, right?
Efficiency is key.
Yeah.
Think about it. The more efficiently we use materials and energy,
Mm.
the lower the cost of producing each item.
Right.
That means more people can afford those items and everyone's standard of living improves.
Right.
Waste reduction is a huge part of that equation.
Yeah, I'm starting to see the bigger picture here.
Good.
So our sources dive into several different manufacturing processes.
Okay.
Let's start with one that's been around for ages.
Casting.
Casting is like the OG 3D printing.
Okay.
You're taking molten metal and pouring it into a mold to create a specific shape.
Uh-huh.
It's a process that's been used for centuries to make everything from delicate jewelry to giant ship propellers.
Wow.
Yeah.
I've always pictured casting as this, super hot and intense process.
What are some of the things that manufacturers need to know about the metal itself
Okay.
to make casting work?
Sure.
It can't just be about melting it down, right?
You're absolutely right. It's a delicate dance between heat and material properties.
Okay.
One thing to consider is the melting point, obviously,
Right.
but you also need to factor in the solidification range,
Okay.
how quickly that liquid metal turns back into a solid.
Interesting.
And then there's the metal's reactivity to gases.
Okay.
Molten metal can absorb gases,
Ah.
which can lead to little bubbles forming within the casting, weakening it.
Huh?
Think of it like a cake that didn't rise properly.
Okay. Yeah, I can see that.
Yeah.
So it's more than just melting and pouring.
Right.
It's about controlling those transformations at a molecular level.
It is.
How do these properties then impact the way manufacturers choose a specific type of casting?
Let's take two examples, sand casting and die casting.
Okay.
Sand casting is like making a sandcastle. You create a mold out of sand, pour in the molten metal, and break away the mold when it's cooled.
Right.
It's great for large objects, but not super precise.
Okay.
Die casting uses metal molds,
Mm-hmm.
which are more expensive to make,
Right.
but you get a much smoother finish and finer detail.
Makes sense.
It's like the difference between baking a cake in a disposable pan versus a fancy bunt pan.
Yeah.
The metal you're working with will determine which method is best.
That makes so much sense.
Yeah.
It's like each metal has its own personality and you have to work with it, not against it.
Exactly.
Do you have a favorite example of something that most people wouldn't think is made by casting?
What's fascinating is that those enormous shafts
Okay.
that help generate hydroelectric power are often made by casting.
Hmm.
We're talking about shafts over 1 meter in diameter
Wow.
and several meters long.
Really?
Casting is the most efficient way to create such massive, intricate components.
Wow, that's not what I pictured at all.
Yeah.
Okay, so we've covered melting metal. Now let's talk about shaping it without melting it down.
Okay.
What's the deal with forming?
Right.
I know blacksmiths do a lot of that.
Yes.
But it's more than just hammering away, right?
Right. Forming is about using force to deform metal into a specific shape.
Okay.
It all comes down to two key properties, yield strength and ductility.
Okay.
Yield strength is like a material's stubbornness, how much force it can withstand before permanently changing shape.
Interesting.
Ductility is like flexibility, how much it can stretch without breaking.
So it's like a metal yoga class.
Uh-huh, exactly.
Are there different types of forming techniques?
There are.
Okay.
We can form metal at room temperature.
Mm-hmm.
That's called cold forming,
Okay.
or at high temperatures, which we call hot forming.
Okay.
Think about a blacksmith heating up metal before shaping it.
Right.
That's hot forming.
Yeah.
It makes the metal more pliable, but can sometimes affect the precision of the final shape.
Interesting.
Cold forming is great for precision, but requires a lot more force.
So again, it's all about choosing the right technique for the job.
It is.
What are some examples of where forming is used in everyday objects?
Think about the body of your car.
Okay.
Those complex curves and shapes are created by forming large sheets of steel, pressure vessels.
Okay.
Those tanks that hold liquids or gases under high pressure
Hmm.
also rely on forming to ensure they are seamless and strong.
Interesting.
Even those graceful curves of airplane wings often start with forming processes.
Wow, I never would have guessed that.
Yeah,
And to think all that shaping is happening at a microscopic level,
it is.
with the metal's grains rearranging themselves under pressure?
Exactly what's fascinating here is that the grains of the metal actually flow during the forming process.
Really?
This creates something called anisotropic properties,
Okay.
meaning the metal ends up being stronger in the direction those grains flowed.
Wow.
It's like aligning a bunch of tiny magnets. They're much stronger when they're all facing the same way.
Okay, my mind is officially blown.
I know, right?
We've got molten metal reshaped grains. What other metalworking magic awaits us?
Oh, there's plenty more to come. Now that we've seen how we can shape metal by casting and forming, it's time to talk about refining those shapes with pinpoint accuracy. That's where machining comes in.
I've always thought of machining as the jewelry making stage of manufacturing, where we take a rough shape and carve it into something precise and beautiful.
That's a great analogy. Machining involves using various cutting tools to remove material from a workpiece,
Right.
creating those precise dimensions and smooth surfaces we need for many applications.
I imagine the hardness of the material plays a big role here.
Oh, absolutely.
You can't exactly carve a diamond with a butter knife.
You're absolutely right. The tool used in machining always has to be harder than the material being cut.
Yeah,
Otherwise, you'll just end up dulling the tool instead of shaping the workpiece.
but machining seems like it would generate a lot of waste, doesn't it?
It can.
All that cutting and shaving must leave behind a lot of scraps.
That's a valid concern. Minimizing waste in machining is something manufacturers focus on heavily.
Okay.
They do this by carefully planning their designs and using sophisticated computer simulations to optimize the cutting process.
Right.
Skilled machinists are also essential because they understand the nuances of different machining techniques and how to get the most out of the material.
So tell me more about these machining techniques. What are some of the most common methods used?
Imagine a potter shaping a clay pot on a spinning wheel.
Okay.
That's similar to turning a machining process used to create cylindrical shapes.
Interesting.
Then there's milling, which is like using a tiny jackhammer to carve away material.
Okay.
It's great for creating more complex shapes and features.
Right.
And we can't forget about drilling.
Of course.
Everyone knows how useful that is for making holes.
It sounds like there's a machining method for just about every need.
Pretty much.
But why is machining often necessary, even after we've cast or formed a part?
Think about the engine in your car. It has tons of moving parts that need to fit together perfectly
Right.
and operate smoothly under intense conditions.
Mm-hmm.
Casting and forming can get us close to the final shape,
Okay.
but for those tight tolerances and incredibly smooth surfaces, machining is a must.
Yeah.
It's the finishing touch that ensures everything works flawlessly.
Okay, so we've cast, formed, and machined our parts.
Yeah.
Now we need to put it all together. What can you tell me about the different ways manufacturers join metal components?
Joining processes are all about connecting those individual pieces to create larger structures and assemblies.
Right.
And just like with every step we've discussed, material properties are critical to getting it right.
I imagine welding is the most common joining method. It's like the heavy-duty glue of the manufacturing world.
You're right. Welding is incredibly versatile and widely used.
Yeah.
It's a process where we essentially melt the edges of the pieces we want to join,
Right.
creating a strong, permanent bond as the molten metal solidifies.
But welding isn't always the answer, right? There must be other methods for joining metal components.
Absolutely. For situations where we can't or don't want to melt the metal, there's a whole category of processes called solid-state welding. It's like a molecular handshake. We use heat and pressure to create a bond at the atomic level without actually melting the materials.
That's amazing.
Eh.
What are some examples of where we'd use solid-state welding?
Think about those massive wind turbine blades.
Okay.
They're often joined using friction welding,
Wow.
a solid-state process where we spin the pieces together so fast that the friction generates enough heat to fuse them.
That's incredible.
Ultrasonic welding, which uses high-frequency vibrations to generate heat and join materials, is another example.
Okay.
You'll find it in everything from medical devices to electronics.
Wow. It's like there's a whole secret world of welding that I never knew about.
There is.
But what about joining methods that don't involve melting the base metals at all?
That's where brazing and soldering come in. These processes use a filler metal with a lower melting point than the pieces we want to join.
Right.
The filler metal acts like a liquid glue flowing into the joint and creating a bond as it cools.
So it's like a gentler, more controlled approach to joining.
It is.
What are the main differences between brazing and soldering?
Think of it like this brazing is for strong, heavy-duty connections, while soldering is for more delicate applications.
Okay.
The key difference lies in the temperature.
Right.
Brazing uses higher temperatures and results in a stronger bond.
Got it.
Soldering with its lower temperatures is often used for things like electronics, where we don't need that super strong connection.
Okay. I think I'm starting to wrap my head around the different ways we can join metal components. But now I'm curious about those processes that go beyond just shaping and joining.
Okay.
How do manufacturers fine-tune a metal's properties to make it even better?
That's where the magic of heat treatment and surface modification comes in. These processes allow us to enhance a metal's properties, making it stronger, tougher, more resistant to wear, or even less likely to corrode.
It's like giving the metal its own superhero origin story.
I like that.
Let's start with heat treatment. I know we touched on it earlier, but I'm ready to dive deeper.
Heat treatment involves using carefully controlled heating and cooling cycles to alter the microstructure of a metal. Think of it like baking a cake. The ingredients are the same, but the way you bake it determines the final texture.
Yeah.
With metal, we're essentially rearranging the atoms within the material to achieve the desired properties.
So what are some of the most common heat treatment processes?
We've got annealing, which involves heating the metal and then slowly cooling it.
Yep.
This relieves stress within the material, making it softer and more ductile, kind of like giving it a relaxing massage.
Interesting.
Then there's hardening, where we heat the metal and then rapidly cool it, often by quenching it in water or oil.
Right.
This makes the metal much harder, but also more brittle.
So annealing is for flexibility and hardening is for strength. What if we need a balance of both?
That's where tempering comes in.
Okay.
It's a process that helps reduce the brittleness of hardened metal, giving us that ideal balance of hardness and toughness.
Right.
We heat the metal to a lower temperature and hold it there for a specific time, almost like a gentle warm-up after a strenuous workout.
Okay, that makes sense. So we've got annealing for softening, hardening for strengthening, and tempering for fine-tuning. Are there any other heat treatment processes I should know about?
There's also normalizing, which involves heating the metal and then letting it cool at room temperature.
Okay.
This refines the grain structure and gives us a good balance of strength and ductility. It's like finding the metal's natural equilibrium.
Got it.
And finally, there's stress relieving, which, as the name implies, helps to eliminate any internal stresses within the metal that might have built up during previous processing steps.
So heat treatment is all about manipulating the metal's internal structure to bring out its best qualities. What about those techniques that focus on modifying the surface of a metal?
Surface modification is like giving the metal a specialized suit of armor, enhancing its surface properties without affecting its core.
Okay.
We can make a surface incredibly hard and wear-resistant while keeping the inside tough and flexible.
What are some ways manufacturers modify the surface of a metal?
One common technique is case hardening.
Okay.
We diffuse carbon or nitrogen into the surface of a steel component, creating a hardware-resistant outer layer.
Interesting.
It's like giving a piece of chocolate a hard candy shell, delicious and durable.
What other surface modification tricks do manufacturers have up their sleeves?
There's a whole world of coatings, from simple paint to high-tech processes like physical vapor deposition, PVD.
Oh.
These coatings can protect a metal from corrosion, reduce friction, or even give it special electrical properties. It's like dressing the metal up for its specific role.
So surface modification allows us to tailor the metal's outward appearance and behavior without changing its inner essence. It's amazing how much control we have over these materials.
It really is. We've come a long way from simply melting and shaping metals. By understanding their properties at a microscopic level, we can manipulate them to create objects that perform flawlessly in all sorts of demanding applications.
I feel like I've learned a lifetime's worth of manufacturing knowledge today. But before we wrap things up, I want to circle back to those economic considerations we touched on earlier.
Okay.
Manufacturing isn't just about making things. It's about making them efficiently and affordably. It's a delicate dance between quality and cost effectiveness.
It is.
Let's dive into that dance in our final segment.
Yep.
Welcome back to the deep dive.
We've explored a pretty mind-boggling array of manufacturing processes.
We have.
From melting and pouring molten metal
Right.
to precisely shaping and joining components,
Mm-hmm.
and even giving them superpower upgrades
Wow.
with heat treatment and surface modification.
It's amazing what we can do with metal these days. And we've talked about, those economic realities of manufacturing.
Yes.
The constant quest for efficiency, sustainability.
Right.
That delicate balance between cost and quality.
It's a balancing act for sure.
Right. We talked about break-even analysis.
Yeah.
But what are some of the other factors manufacturers consider when making decisions about which processes to use?
Well, one of the biggest factors is production volume.
Oh,
If you're making a small batch of specialized parts,
mm-hmm.
let's say custom components for a high-end sports car,
Okay.
then processes like machining or 3D printing might be the most economical, even if the per unit cost is higher.
Right.
But if you're churning out thousands of identical parts, like
Yeah.
door handles for mass-produced cars,
Right.
then processes like casting or forming, which have higher upfront costs but lower per unit costs, become more appealing.
It's like choosing between a craft artisan and an assembly line.
Exactly.
It all depends on what you're making and how many you need.
Precisely. Another critical factor is material utilization. Minimizing waste isn't just good for the environment.
Right.
It's good for business. The less material you waste, the lower your costs.
Makes perfect sense. What are some ways manufacturers reduce waste in the manufacturing process?
Design optimization is key.
Okay.
Using computer simulations, engineers can design parts that use the least amount of material while still meeting strength and performance requirements.
Right.
Think of it like building a bridge.
Okay.
You want it to be strong enough to handle the traffic, but you don't want to use more steel than necessary.
So it's about finding that sweet spot between strength and efficiency.
Exactly. Process optimization is also crucial.
Okay.
For example, fine-tuning machining parameters can significantly reduce the amount of material removed, minimizing waste and saving money.
It sounds like manufacturers are constantly looking for ways to squeeze every bit of value out of those precious resources.
Absolutely. And we can't forget about labor costs.
Right.
Automation is transforming the manufacturing landscape, reducing the need for manual labor, and often leading to increased efficiency and lower costs.
Right.
However, it also creates a demand for skilled technicians who can operate and maintain those sophisticated automated systems.
It's fascinating how technology is changing the face of manufacturing, bringing both challenges and opportunities.
Indeed. And speaking of challenges, energy consumption is a big one.
Yeah,
All those furnaces, machines, and robots require a lot of energy.
that's true.
Manufacturers are increasingly focusing on energy efficiency,
Okay.
adopting technologies like high-efficiency furnaces, intelligent lighting systems, and even exploring renewable energy sources like solar and wind power.
It sounds like sustainability is becoming a core principle in the manufacturing world.
It absolutely is. Consumers are demanding more environmentally friendly products, and manufacturers are responding by incorporating sustainable practices into every stage of the production process.
This deep dive has given me a whole new perspective on manufacturing. It's not just about making things. It's about making them smarter, more efficiently, and with a growing awareness of our impact on the planet.
I'm glad to hear it.
Yeah.
As you go about your day, I encourage you to look at the objects around you with a newfound appreciation for the intricate processes and the human ingenuity that brought them to life. Every object has a story to tell, a journey from raw materials to finished product that often involves a remarkable blend of science, engineering, and artistry.
It's like a hidden world that we often take for granted.
Exactly. So next time you pick up your phone, drive your car, or even just sit in a chair, take a moment to think about the incredible journey those objects have been on and the countless hands that have shaped them along the way.
That's a great takeaway.
Okay.
We've covered a lot of ground in this deep dive,
We have.
but I feel like we've only just scratched the surface of this vast and fascinating world.
There's always more to explore, more to discover, and more to learn about the ever-evolving world of manufacturing.
Until next time, keep those gears turning, those furnaces burning, and those minds exploring. Thanks for joining us on the Deep Dive.